Okay, moving on to the next section, which is section 5.3 for us. And we're going to combine day 1 and day 2 into um, one day here. So inverse functions. What we're going to eventually be doing is looking at the derivative of the inverse function. And before we do that, I'd like to just do a quick review of inverse functions, things that you learned in pre-calc and advanced algebra. So definition of an inverse function, a function g is the inverse function of the function f of x if f of g of x equals x for each x in the domain of g, and g of f of x, where equals x for each x in the domain of x. The function is denoted by f inverse of x, and that's what we're saying. Let g of x equal this inverse of f. So there is common notation. F to the negative 1 is what it looks like, doesn't it? But we read it as f inverse of x. There is a reflective property of the inverse function. If I have one of these graphs, let's just say this is my f of x, my original graph, then the graph of f contains the point AB. Let's find a point on AB here, or on f. Label it, what would this be? 2, 0. That's my AB. And then it says the graph of f contains the point, for us, 2, 0, if and only if the graph of f inverse, here's my f inverse graph, contains the point b comma a, or just the reversal. So if I reverse the x and the y, I'm going to get out 0, 2. And now it's in the format of b comma a. That is a characteristic of inverse functions. You'll also notice then that every ordered pair takes on that ability of the original function was AD. Well, then the inverse function is going to be an ordered pair B comma A. It also reflects over this line y equals x. That becomes the line of reflection, and these points should end up being right angles to the line of reflection, as well as being congruent distance, equal distance apart from the line of reflection, and we see that happening. So that's very characteristic of inverse functions. The example number 1 says, in the graph f of x equals 2x cubed plus 2, what is the equation of the inverse? Verify that the functions are actually inverses of each other. So let's go with, we have the function f of x equals 2x cubed plus 2. How do I find an inverse? Find the inverse by swapping, however you want to think of it, switching x and y, then solve for y. That's a procedure that you have done before, I'm sure. So I'm going to start with, I've got y equals 2x cubed plus 2. And that was my f of x. To find the inverse function, f prime of x, I am going to switch my x and y. So this will now say x equals 2y cubed plus 2. Okay, continuing on with this, we're going to keep solving for y. And let's see, we go x minus 2 equals 2y cubed, divide by 2. And we got x minus 2 over 2. Take the cube root, y would be equal to the cube root of x minus 2 over 2. Now that is our inverse function. So I'm going to go ahead and rewrite this. We have where this was f of x, this is f inverse of x. Turns out to be the cube root of x minus 2 divided by 2. So what they asked us to do was to verify that these functions are indeed inverses of each other. Do you know how to do that? Well, this definition of an inverse describes it for us. It said a function is an inverse if f evaluated at g of x equals x, and the reverse is true. So what I got to do is do a composite function f of g, see what I get there. I should get x, and g of f, I should get x. So let's see if that's true. We want to build f of g of x, where this is our g of x, the inverse. So to insert for x, cube root of x minus 2, our g of x function, plus 2. Oh, this gets cubed, doesn't it? There's that cubing. Now, cube root taken to a third power kind of dissolves the cube root being cubed. So I get 2x minus 2 over 2 plus 2. This is like 2 over 1. 2 cancels into 2, and I get x minus 2 plus 2 gets us f. So we've just verified that f of g of x is equal to x. But that's not enough. We also have to do the reversal. So let's reverse this. G of f of x should also turn out to be x. So now we're starting with our g function, which is the cube function. Where I see x, I replace it with my f of x. So 2x cubed plus 2 minus 2 over 2. Here's that f of x coming in. What do I want to say? The parentheses are not really necessary. I guess that's on a wide, we'll undo that. But the parentheses aren't really necessary. They are not really serving much of a purpose other than to identify a plugged in f of x. So I can really look at, sorry about that, I can really look at 2 minus 2 and say that's going to go to 0. And that leaves me a cube root of 2x cubed divided by 2, cancel our 2's, and we get the cube root of x cubed, simply would be x. Hey, this one works out as well. So we've just verified both ways. G of f of x and f of g of x both end up being value of x. Therefore, they are inverses. A function has an inverse function if and only if it is 1-to-1. What does 1-to-1 mean? Man, math gets complicated, doesn't it? 1-to-1. 1-to-1 is a special type of function. It means for every x, there is exactly 1 y. And for every y, the reverse is true here. Every y, there is exactly 1 x. So it's a little bit stronger than just being a function. We know functions, let's just kind of sketch out a cubic function here. Cubic function, does it pass the vertical line test? Well, if I take my vertical line and slide it, yep, only ever striking once, which really is a test to say that for this particular x value, I get out one particular y value, right? Every x has 1 y. But now a 1-to-1 function says for every y, there's exactly 1 x. It works in the reverse as well. So a 1-to-1 function, it passes the vertical and horizontal line test. And if that's true, then there is an inverse function. Okay? If f is strictly monotonic on its entire domain, like that cubic function was, either increasing all the time or decreasing over the entire domain, then it is a 1-to-1 function and therefore has an inverse function. So cubic function, a great example of monotonic. Now, how could I use calculus to determine if something is monotonic? Well, I can use calculus because I can look at its derivative. If I look at the derivative and it's always greater than 0, or maybe even equal to 0, then I know I've got an increasing function. And this would be, if this were happening over the entire x values, it's a monotonic function over all reals, increasing everywhere. If my first derivative was less than or equal to 0, it's a decreasing function over whatever interval, maybe all reals that we're talking about. Hey, so good question here. Let's take that y equals x cubed example. If we take the derivative, what do we get? Well, we get 3x squared. That's its derivative. Is 3x squared always positive? Well, when things get squared, they are, aren't they? And if I multiply by a plus 3 here, which I am, I know that this thing is always an increasing function. Hey, we just proved that a cubic function is monotonic because it's increasing all the time. Its first derivative shows it. All right, example 2. Find the inverse of the function, state the domain and range of the function, and its inverse. Okay, so the domain of this function. Well, I've got to make sure that this stays positive underneath the square root because I am not working underneath the imaginary number system or the complex number system. We are strictly held to the real number system in this AP Calc class. So in order for that to happen, I need x minus 3 to be greater than or equal to 0, which means that x will be greater than or equal to 3 for that to happen. So if I put this in set notation, it says the set of all x is such that, that's that straight line, x is greater than or equal to 3. The range that comes out, well, if I'm looking at this, I'm looking at a principal square root, the positive, right? And that would then tell me that my y values are always going to be greater than or equal to 0. They're always going to be positive. I know if I plug in 3 for x, I will get out 0. So no denying that we could get a 0 out. So there's our range. Here's our domain. The inverse function. Well, we've got y equals square root x minus 3. If I flip-flop my x and y's and solve, we'll get our inverse function. So this is finding the inverse. Solve for y. Let's square both sides. Add the 3 over. We're going to get y equals x squared plus 3. There's my inverse function. Now, the range from the original function becomes the domain for the inverse function. Remember how this had an ordered pair of AB? Switching for the inverse, it becomes a BA. The range from the original function becomes the domain. So I will now have x values that are greater than or equal to 0. And the domain from the original function will become the range for the inverse function. So my y values are going to pick up the old domain. Oops, that should be x there. This will be a y has to be greater than or equal to 3. Let's just, you know what, let's plot a couple points here. We got the point 3, 0, and we know that's the AB, so it's going to flip to a BA for the inverse and become 0, 3. This point 7, 2 also switches and becomes 2, 7 on the inverse function. If I draw my line through that, there is the inverse function. So this is f and this is f inverse. Now, does it make sense if we go back here and look at what we call the domain, all x values greater than 0? So I'm looking, here's x being 0, and I can travel to the right. Yep, my curve definitely carries those x values, x being greater than or equal to 0. My y values don't start until 3, and then they get larger. So indeed, our range makes sense. Now, this certainly looks like a parabola. And I'm asking myself, well, what happened to the other side of the parabola? Well, under this condition, when we're making our inverse function, remember we had some restrictions. Our domain is the x values greater than 0. So this left branch of the parabola would involve negative x values, and we are not dealing with those. We're only looking at the positives. So, story told. Now let's get into the calculus part of this, the derivative of an inverse function. Let f be a function that is differentiable on the interval. If f has an inverse function g, then g is differentiable at any x for which f prime of g of x is not equal to 0. The reason that we have to have this in here is because for us, the definition of the derivative of the inverse involves putting the derivative of the f function evaluated g of x. And we would not want this to turn out to be 0, because then I'm trying to divide by 0. So there's one stipulation here that we cannot have f prime of g of x equal 0. Now, this could also be written as an inverse. So the derivative of f inverse evaluated at x is equal to g prime of x. This is just talking about the inverse notation. Another goal, how do we find the derivative of the inverse function? Well, what we're going to try and do is come up with a way to find the derivative without having to first calculate the inverse. So if I have f, I don't want to have to go solve this first and find f inverse and then take the derivative of my f inverse, because sometimes finding inverses is not the easiest. So maybe I can get around not having to do it if I can find an alternate method. And that is what the instructions here detail. Let me take you through an example, and there's those details. Our function is not just a nice parabola. And I know on your worksheet or your note sheet, you have this point. Let's pretend we don't even see that. And my instructions are going to be to find g prime at 4, where x is 4 for the g function, for the inverse function, right? For the inverse function g of x. That means I have 4 comma, well, I don't know, because I don't even have the inverse function really, right? I didn't solve this out and come up with the inverse function, because we said we were going to try to avoid doing that, although it is a possibility. What I can do is use f of x to find my ordered pair. I can come up with some a value here. And remember how a comma b gets flipped to b comma a? Well, if I can solve it here, then I can place it into there. So that's our notion. We're going to go about that. Well, first let's just find f prime. F prime, super easy. F prime of x is 2x, taking the derivative of x squared. Okay, so bank that, we have it. Now, let's take what we were describing about finding the unknown value. Let's set our original function equal to 4. So x squared equals 4, which means that x is equal to plus or minus the square root of 4, which means x is equal to plus or minus 2. But we want all x values that are greater than 0, so we're going to just keep our positive 2, okay? Now, this tells me that I have an ordered pair of 2, 4 for the original function, doesn't it? When I solved, this was my y value. When I solved for x, I got 2. That means then this is the ordered pair AB. I can flip-flop this and make this BA. And I get 4 comma 2. All right, that helps. Now we're going to use this notation here, and we want to find g prime of 4, which is like saying f inverse, no, I'm sorry, the derivative of f inverse of 4, and that's like 1 over f prime of a. F prime of a. Its a value is 2. Okay? So what I need to do is I need to evaluate at g's range, which is like f's domain. And did we already do that work? No, we haven't. Let me do that quick then. F prime of 2 goes back to, I know my function, it'll be 2 times 2, which gives me 4. And replace that, we get g prime of 4. The inverse function evaluated at 4 is 1/4. Very nice. Letter B. We're going to ignore once again this ordered pair. It was 1, 5. Let's see if we can figure out why 1 was there. I want you to find the inverse derivative at 5. Okay, this is G's domain. 5 is in G's domain. I wonder what its range was, because its range becomes the domain for f of x. So one thing we will have to find is f prime of x. So I'm going to just go ahead and get that done. F prime of x is 3x squared. Let's find this x value here. So I can say that f of x is equal to 5. Or 5 is equal to, where is f of x? Right here. X cubed plus 4. Subtract 1, that would give us x cubed equals 1. Take the cube root, x is equal to 1. Aha! 1, 5 is our ordered pair. That means 5, 1 is an ordered pair on the inverse function. And since I want to find the inverse derivative at 5, that's going to be like, I want g prime of 5. That's like saying I need 1 over f prime of 1. The domain for g is the range, let's see, how do I want to say that? The domain value for g is the range value for f. So now I need its input value of 1. And that means then I need to evaluate f prime at 1. We already knew that it was a 3x squared for its derivative. Throw in 1, square it. We're coming out with 3. This will end up being 1/3. Not so bad. I think if you lay it out in this context, this notion of keeping straight the ordered pairs and how they're different for an inverse function versus an original function is key. And then this step 3, knowing this relationship. Really, the derivative of the inverse function is the reciprocal of a corresponding ordered pair of the original function. So they have a reciprocal relationship. This one here is a great example of, you know what, trying to find your inverse function would be quite difficult. Just think, if we switched our x and y's and tried to solve for y, finding that inverse would be extremely difficult, wouldn't it? So having this method of being able to do it without finding the inverse function and then taking the derivative of the inverse function is key. So f's ordered pair, we know we want to find g prime of 1. We want to find the inverse function evaluated at 1. So f prime of x is equal to 2 minus sine of x. We know the ordered pair. The ordered pair was 0, 1. So for f of x, it's 0, 1. For g of x, it's a 1, 0. They have that ABBA relationship. Let's find f prime of 1 then. F prime of 1 is 2 minus the sine of, sine of 0. Almost the C in 1, and I was stunned there a minute. 2 minus 0 then, sine of 0 is 0. We get 2. F prime of 1 is 2. To find g prime of 0, did I do this backwards? I sure may have. We wanted g prime of 1. Uh-oh. I got to go back and step this out. Oh, I did. I just wrote it wrong up here, didn't I? Sorry about that, guys. Go back. We were finding f prime of 0. And then I put sine of 0 in. And it was just my notation on the left was wrong. The calculation on the right was fine. All right. Because I need to look at that ordered pair. So we were evaluating at 0. That gives us then a clue about the derivative of g evaluated at 1. It's 1 over the reciprocal here of f prime of 0. And f prime of 0 we know to be 2. So it's a 1/2 for the inverse relationship. One more problem. D, find g prime of -1, where g of x is the inverse of f of x. So I want to find g prime of 1. That's going to be a 1 over f prime of something. Okay, so for g, it's -1 something. Ooh, I don't know it. So I can find this. I can find f of x equals -1. What input gives me an output of -1, right? Well, go to the table. We have f of x on our table. F of x, I see -1. It corresponds to a value of 3. The x value is 3 to get -1. So I get an ordered pair of 3, -1. 3, -1 is our f of x. That means -1, 3 is my g of x. Okay, well now we can come back to this question and finish it. G prime of 1 is equal to 1 over f prime of 3. 1 over f prime of 3. Look at the table. Look that up in the table, just like we did on the other one. Now I got to read my table just a little bit differently, right? I need to find 3, got it, and I need to find its derivative. The derivative of 3 is -4. So we get -1/4. I like the tables. Tables are good. Okay, continuity and differentiability. If f is decreasing on its domain, then f inverse is decreasing. That's kind of cool. If f is increasing on its domain, then f inverse is increasing. If f is continuous, f inverse is continuous. So just some good things to know. If f is differentiable at c, and we know that f prime of c is not 0, such that a derivative exists at that c, then it will be differentiable as well. So just some good things to keep in your head. If one is increasing, then the inverse is increasing. Use the derivative to determine whether this is monotonic. Well, it's cubic, but it's got a little bit more, doesn't it, on its entire domain and therefore has an inverse. Okay, so if I want to talk about monotonic, I want to know something about its derivatives. I need to know slope info. How do I get slope info? I get slope info off a derivative. The first derivative, matter of fact. So f prime of x would be 3x squared plus 5. And you're probably thinking, well, that doesn't really help me a lot. If I had a domain of negative infinity to positive infinity for my x value, would this be positive? Well, certainly this term is always positive, right? Square something and we get positive. And then we're adding 5, adding a positive. So a positive plus more positives gives us always positive. Could we have a 0? We could. Oh, no, 0 goes in and we get 5. This thing is always greater than 0. So the derivative is always greater than equal to 0. I'm not even sure it could be equal to 0, but we'll just say it's greater than 0. Therefore, f of x is monotonic. It's always increasing. F of x is increasing. So easy to use first derivative to talk about monotonic functions. If g is the inverse, and we know that f of 3 equals 2, find the value of g prime of 2. Okay, this is a lot like what we were just doing. They gave us an ordered pair, didn't they? They said f of 3 equals 2. That gives me an ordered pair for f, which immediately now I know g of 2 gives me 3, right? I can reverse the ordered pair. The domain becomes the range becomes the domain for original functions to inverse functions. And they want g prime of 2. Well, that's pretty easy. It's 1 over f prime of 3. And do I know f prime of 3? Nope, I'm going to have to take a derivative, aren't I? 3x squared over 4 plus a 1. And we need to evaluate it at 3. 3 times 9 divided by 4 plus 1. 27 fourths plus 4 fourths gives us 31 fourths. Okay, so this is 1 over 31 fourths, which gives us 4 over 31. Reciprocal relationships. All right, that takes us to homework. I I think you'd get enough practice on these early ones if you just did the odds. So just focus on those odds 1 through 7. Once you get down into the derivative work, let's continue 9. Let's do all of these in this assignment that follows from 9 on out. Okay, excellent.